Hi there. In today's episode of Member of the Public, we're going to have a look at special relativity. But we're not going to use trains passing each other, with people staring out of windows trying to synchronize their watches. No, we're going to do this the proper way, in outer space. Because that's the only place where we can find the huge distances and also the huge speeds at which the effects of relativity become noticeable. But before we do that, we first need to know about one definition and two axioms.
First, the definition. An inertial observer is someone who is not subjected to acceleration. You undergo acceleration if you move along a curve instead of a straight line, or if your speed slows down or increases. Gravity too causes acceleration, so even if you sit down on a chair at home, you're not an inertial observer. So strictly speaking, it's hard to find someone on Earth who is an inertial observer. In contrast, in outer space, far away from any gravity field, it's fairly simple to be an inertial observer. All you need to do is be either at rest or move at a constant speed and in a straight line. Now, our first axiom. To different inertial observers, no matter at what speed they are moving, the speed of light always has the same value of 299,792,458 meters per second, or about 300,000 kilometers per second. Provided, of course, that the light is not slowed down by a medium, like air or glass. This may sound rather unremarkable until you really think about what it means. Imagine you're at an airport terminal and you watch an airliner roll by at a steady 80 meters per second. The beams of the plane's landing lights point straight down the runway. If someone asked you at what speed relative to you the light beam leaves the landing lights, you would be inclined to say the speed of light plus 80 meters per second. Well, according to our first axiom, that's wrong. The speed of light is the same to all inertial observers. If for a moment we make abstraction of the Earth's gravity field and the effect of air on the speed of light, both you and the pilot are inertial observers. You are at rest and the pilot is moving in a straight line and at a constant speed. Now, the second axiom states that if multiple events happen simultaneously at the same place to one observer, they happen simultaneously at that same place to all observers. So if you drop a bowling ball on a dinner plate, the event of the ball hitting the plate and the event of the plate breaking will happen at the same time and place. Not only to you, but also to the pilot of a plane passing 10 kilometers overhead. Though the time at which the pilot perceives the two events happening may, because of relativity, be slightly different from yours. Now you understand that using examples of trains, planes or cars can sometimes be confusing, if only because of the Earth's gravity field. So plenty of reasons to move our experiments into space, where you can imagine observers to be far away from any gravity field, and where there is no air to play havoc with the speed of light.
One last thing before we start. The difference between special relativity and general relativity is that special relativity only considers observers that are inertial observers. So people that are either at rest or move at a constant speed in a straight line. And this hugely simplifies things. And it's also the reason why Einstein first developed special relativity in 1905. And then, 10 years later, in 1915, general relativity. But don't worry. This episode will be only about special relativity. See you at the other side.
It's Fleet Day at Space Fleet. Time for all squadron leaders to show off their skills to the Space Fleet Admiral. She has parked her flagship somewhere in space, which we will indicate with this cross. All the fleet's squadrons are to fly past the Admiral. Now, there's one squadron leader who really wants to impress her. He's going to show how good his crew is at high-speed precision flying. This is what he plans to do. His squadron consists of 3 spaceships. The squadron leader rides in the rear ship, Spaceship 3, so he can keep a close eye on what his squadron is doing. He's going to have the squadron fly past the Admiral in single file, one after the other, so close that they will almost take off her antennas. And this at the dazzling fly-past speed of 25% of the speed of light. The spaceships will fly in absolutely rigid formation, keeping a distance of exactly 1 light second between them. 1 light second is the distance light travels in a period of 1 second. So that's about 300,000 kilometers. This is what that will look like. But the squadron leader is really eager for a promotion. So he's going to combine his flypast with an awesome light signaling demonstration. When his ship, Spaceship 3, passes the Admiral, it will send out a light beam to Spaceship 2. At exactly the same time, Spaceship 1 will also send a light beam to Spaceship 2. Now, how does Spaceship 1 know when to send its light beam? Well, that's simple. Spaceship 1 knows that Spaceship 3 follows at a distance of 2 light seconds. Because the flypast happens at 25% of the speed of light, that means that Spaceship 3 will pass the Admiral 8 seconds after Spaceship 1. So all Spaceship 1 needs to do is send its light beam 8 seconds after it has passed the Admiral. And the 2 light beams will be perfectly synchronized. They will leave the 2 spaceships at exactly the same moment. And that moment is when Spaceship 3 passes the Admiral.
Now that we have a clear idea of what the experiment looks like, let's see what it actually produces. To do that, we'll take a slightly more mathematical approach. But again, no worries. There will be a few formulas.
This diagram shows the position of the 3 spaceships and the Admiral, both in space and in time. From the observation point, in relativity speak, the frame of reference of the squadron leader. It's called a space-time diagram. Note that the time unit is seconds, and the distance unit is light seconds. Remember, a light second is about 300,000 kilometers. As soon as we start the animation, you'll see that the squadron leader won't be moving. Because the diagram is set up according to his frame of reference, he and his spaceship will stay at the 0 distance point. The spaceships are set 1 light second apart on the space axis, because that is their fixed mutual distance in the squadron flight formation. You can actually think of the space axis or distance axis as the flight path the spaceships will be following through space. And the Admiral sits, of course, along this path. We have already defined 0 distance as a place where the squadron leader will be, from his point of view, throughout the flypast. But what is 0 time? Well, 0 time is defined as the moment Spaceship 3, and therefore the squadron leader, passes the Admiral, which is also the moment at which Spaceship 3 and Spaceship 1 will send their light beams to Spaceship 2. The 3 vertical lines that cross the position of the spaceships are their speed lines. They are vertical because the spaceships are not moving relative to the squadron leader. If you take, for instance, Spaceship 2, no matter which point in time you consider, Spaceship 2 will always be at 1 light second away from the squadron leader. In the same manner, the orange line represents the relative speed at which the Admiral will be approaching the squadron leader. Remember, we are looking at things from the frame of reference of the squadron leader. To him, it will be as if the squadron stays put, and it's the Admiral who is approaching at 25% of the speed of light. That leaves us with the yellow lines. They are none other than the speed lines of the light beams that will be shot out by Spaceship 3 and Spaceship 1 at time 0, when Spaceship 3 passes the Admiral. Now, let's have a look at the speed line of light beam 3. Why is it drawn that way? Well, a light second is per definition the distance light covers in 1 second. So if you let the beam run during 1 second, it will have covered exactly 1 light second, which leads us to this point in space-time, which incidentally is also the position of Spaceship 2 throughout time. All we need to do to draw the light speed line is connect the 2 points. Because the visual unit lengths are chosen in such a way that the unit grid consists of perfect squares, we can construct the light speed line in an alternative way, as a line that departs from Spaceship 3 at a 45-degree space-time angle. We can apply the same method for drawing the light speed line of light beam 1. Only this time the slope is negative. That is because light beam 1 will be sent rearwards. This may all sound complicated and confusing, but the animation will immediately make things much clearer. The animation starts with Spaceship 3 being at a distance of 3 light seconds from the Admiral. So that's about 900,000 kilometers. Flying at 25% of the speed of light, it will take exactly 12 seconds to reach the Admiral. Here we go. Spaceship 1 passes the Admiral. Spaceship 2 passes the Admiral. And light beam's gone. We'll watch that again step by step. Let's start where and when Spaceship 2 has just passed the Admiral, because before nothing really significant happens. So Spaceship 3 is approaching the Admiral. Watch the pink time marker coming into view as we get closer. There we are. We have reached the time-space 0 point, where and when the squadron leader, who rides in Spaceship 3, passes the Admiral. And also where and when Spaceship 3 sends off its light beam to Spaceship 2. And of course, at the same time, but at a different place, 2 light seconds away from the squadron leader, Spaceship 1 sends off its light beam. We can trace the heads of those 2 light beams all the way to the point in space-time where they cross the speed line of Spaceship 2. This is where and when they are received by Spaceship 2, 1 second later, after each having traveled a distance of 1 light second. Okay, this was the fly past as seen from the frame of reference of the squadron leader. Let's see what that looks like from the frame of reference of the Admiral. Again, we have a space-time diagram, but this time around it's from the frame of reference of the Admiral, instead of the squadron leader. For the time being, just ignore this green line. So the Admiral sits at the 0 distance point, and it's the squadron that will be doing the moving. This frame of reference is actually the frame of reference from which the whole experiment was set up. The spaceships are doing the flypast, not the Admiral. The 0 time point has remained the same. It's still defined as the moment Spaceship 3 passes the Admiral. Remember those vertical speed lines of the spaceships? They are now slanted to reflect their relative speed to the Admiral, a speed of 25% of the speed of light. Simple physics, right? Unfortunately, no. Already we have to take into account a really weird relativity phenomenon. Relativity not only affects perceived time, but also perceived space. In the eyes of the Admiral, the distance between the spaceships has shrunk. The faster the spaceships fly past, the more that distance shrinks. Actually, the spaceships themselves and the crew inside also shrink in the eyes of the Admiral, along the flight path. But because we have represented the spaceships as mathematical points, that shrinking does not appear in the diagram. The squadron leader won't experience this shrinking effect. To him, the distance to the next spaceship, and for that matter, the length of his spaceship or his own shape, stays exactly the same. This effect was discovered by Henrik Lorentz. We are not able to deduct it from the graph, so we have to take Lorentz's word for it. At a flight path speed of 25% of the speed of light, you have to reduce the distance between the spaceships and also the size along the flight path of the spaceships themselves and their content, including the squadron leader, with a factor of about 1.03 in order to get the distance the admiral perceives. This factor is called the Lorentz factor. 1 divided by the Lorentz factor is about 0.97. The Lorentz factor is calculated using as input the speed between the two frames of reference relative to the speed of light. In this case, v is equal to 25% or 0.25. That gives a value of about 1.03. The consequence of this is that our spaceship speed lines are wrong. Their angle, in other words, their speed, is still okay, but the implied distance between the spaceships is not. We can adjust that distance by applying the Lorentz factor. In this case, 1.03. So the distance between the spaceships has shrunk to about 97% of 1 light second. And that's indeed what the Admiral sees. By the way, the Admiral herself is also represented by a mathematical point. What's more, there are no other fixed points in her frame of reference. That's why in the previous diagram, the one with the squadron leader as frame of reference, there was no space or distance to apply space contraction to. So space contraction has no effect on speed. In other words, our axioms remain valid. That means that when the squadron leader flies by and shoots off his light beam, the Admiral will not see that light beam travel at 125% the speed of light, but just at 100% of the speed of light. That means we can still draw the speed line for the light beam that leaves Spaceship 3, as observed by the Admiral, at an angle of 45 degrees. The question is, to what point do we need to draw that speed line? Well, to the point in space-time where the light beam and Spaceship 2 meet. And that point is right here, at the intersection of the two speed lines. This is where the second axiom comes in. If to the squadron leader the light beams sent by Spaceship 3 and Spaceship 1 arrived at Spaceship 2 at the same time, then they should also arrive there simultaneously in the eyes of the Admiral. That means that from that light reception point in Spaceship 2, we can draw the speed line of light beam 1. And don't forget, according to axiom 1, it also runs at an angle of 45 degrees. How far do we have to draw? Simple, till the line intersects the speed line of Spaceship 1. We have found the point in space-time where and when Spaceship 1 sends its light beam. That is, in the eyes of the Admiral. Now we are finally ready to run the simulation. Spaceship 1 passes the Admiral. Spaceship 2. And light beams away. We'll do it again, step by step. Spaceship 3 is coming up on the Admiral. Watch the pink time marker. And we're at time 0. Time and place where and when Spaceship 3 passes the Admiral. And also where and when light beam 3 is sent. Let's move on in Admiral time, to the point where Spaceship 1 sends its light beam. Amazingly, in the eyes of the Admiral, light beam 1 is only sent about 0.52 seconds after the squadron leader has passed her, and at a distance not of 2 light seconds, but of 2.07. Luckily, she's well versed in relativity theory. Otherwise, she would later tonight at the Space Cadet Ball give the squadron leader and his crew a good dressing down for botching their synchronizing maneuver. Let's continue to the point where, according to the Admiral, Spaceship 2 receives the 2 light beams. So apparently that's about 1.29 seconds after the squadron leader has passed the admiral, and at a distance of about 1.29 light seconds. Remember, to the squadron leader, that value was not 1.29, but 1. Now, let's revisit the time-space point where Spaceship 1 has sent its light beam. In the squadron leader's diagram, this point has coordinates 2 light seconds and 0 seconds. We also know where the squadron leader's 0 point for time and space is, at the same spot as the admiral's, right here. Therefore, if we draw a line between these 2 points, we have in fact drawn the space axis of the squadron leader. We can then immediately indicate the unit of space on that space axis, as it must be halfway the 2 light seconds. Furthermore, we know that the light beams reach Spaceship 2 after 1 second in the eyes of the squadron leader. So if we draw a line segment parallel to the squadron leader's space axis, with a length of 1 light second, we must arrive at the unit point for seconds on the squadron leader's time axis. If we connect that point with the space-time 0 point, we get none other than the speed line of Spaceship 3. So the speed line of Spaceship 3 is the squadron leader's time axis. Though the diagram of the squadron leader is completely skewed, it still shows that the first axiom remains valid for the squadron leader. He sees the light beam cover a distance of 1 light second in 1 second. So the standard speed of light. As a recap, the green lines represent nothing else than the frame of reference of the squadron leader. Space contraction has become clearer now. If we place both the admiral and the squadron leader at their time-space 0 point, we can see that to the admiral, Spaceship 2 is at 0.97 light seconds, whereas to the squadron leader, it is at 1 light second. And finally, we can demonstrate the time effect of relativity, which is called time dilation. If 1 second has passed for the squadron leader, 1.03 seconds have passed for the admiral. In the eyes of the admiral, the squadron leader's time is moving slower. In other words, in the eyes of the admiral, the squadron leader ages slower. Bizarre, but true. And yes, that ratio of 1.03 is again the Lorentz factor. So the Lorentz factor calculates both space contraction and time dilation.
I hope you enjoyed this brief excursion into the wonderful but mesmerizing world of relativity. If you're interested, there's some more references down below in the description. As for now, see you next time, whenever or wherever that may be. Bye bye.